This is a nice visual here of the properties of waves, so with some visual for some key terms. Peak is the top or the crest. Notice that midpoint here is that horizontal line. Trough is the bottom. Amplitude is the distance essentially from the midline to the top of the crest or the bottom of the trough. And the wavelength is from trough to trough or measured from peak to peak. So let's look at light wavelengths, I should say. Light waves are a form of electromagnetic radiation energy that travels through space as an oscillating electric and magnetic fields. Unlike sound or water waves, light doesn't need a medium to travel. Key difference there. Light waves are regarded as varying electrical fields coupled with varying magnetic fields at right angles to each other and the direction to travel. So here's just a mechanical wave, and that's how we may think about these, but light waves actually have these multi-directionalities to them. Makes them a little bit more complex, which is why I need to go over and understand some of these key terms. So those for example, those transverse waves, the electrical and magnetic fields oscillate perpendicular to the direction that the wave travels in, and this transverse nature allows light to be what we call polarized, which means we can filter and align the directions of its electrical field. You can see example here of a polarizer eliminating out some of those wavelengths there and getting into basically just one there. Now if we have a polarizer, it's kind of at a right angle, we could see we might eliminate all the wavelengths. How this might relate or how you might be exposed to this without even realizing it is polarized sunglasses. So if we're looking here at the water where all this light's kind of coming back at us and developing that glare, makes it very hard to see into that water. However, if we have polarized sunglasses, it might eliminate certain wavelengths there, allowing the glare to be reduced and then able to see deeper into the water. If you do have polarized sunglasses and you tilt your head, you might see varying amount of glare developing. And that's basically rotating your glasses. That's basically rotating the polarization there. So a great way to kind of go about and test it out for yourself to see this in action. Now those key wave properties are amplitude, wavelength, frequency, period, as well as speed. And we could see them all quickly summarized in the table right below here, but we're going to talk about these in a little bit more detail here to give you some relation and a deeper understanding of them. Wavelength, again, the distance between identical points are consecutive waves. Amplitude is the distance between the origin and the crest or the trough. Frequency is the number of waves that pass through per unit time, and speed is wavelength times frequency. We can kind of see them all described here. Let's start with that amplitude. Let's get into this one in a little bit more detail. It refers to the maximum strength of the electrical and magnetic fields that make up the wave. It quantifies how intense or energetic the wave is, but does not impact the color of the light. Key aspect there. Larger amplitude does mean that the wave carries more energy and will appear brighter. So here we can see the example of like a dimmer switch increasing the amplitude. Smaller amplitude means less energy and essentially dimmer light. So again, we can see how it looks on the wave here. We can also see how we would visually interpret a greater, larger, or a smaller amplitude. Think of a light being dimmed. Then we get into wavelength. This is probably the most obvious, and wavelength in light waves refers to the distance between two consecutive peaks or troughs of the electromagnetic wave, represented by the Greek letter lambda. This determines the color of the light. It is measured in nanometers for visible light. Sorry, this is light over there. So as we can see, the different nanometers or different wavelengths of light correlate with different colors. Those longer wavelengths are going to be more your red and orange spectrums, and those shorter wavelengths are going to be more your violets and your blues. And this brings us, of course, to frequency. So frequency in light waves refers to how many wave cycles pass through a point in a given second, and this determines the energy and color of the light. Measured in hertz, 1 hertz essentially means 1 cycle per second. Now I just told you again, those wavelengths directly relate, yes, but also frequencies also correlate with those colors. And this is the reason for this is because the speed of light is fixed. So wavelength and frequency multiplied together essentially directly impact the speed of light. And as wavelength increases, frequency decreases. And as wavelength decreases, frequency increases. So this is what we call an inverse relationship between our frequency and our wavelength. Now, when we look at the period of light waves, this refers to the time it takes for one complete wave cycle to pass a given point. This is the inverse of frequency. Frequency tells us how many cycles occur per second. Period tells you how long each cycle lasts. It's represented by the symbol t. Its units time is seconds, and the formula is t equals 1 over f, where t, again, is the period, f is the frequency in hertz. We see a visual representation of showing you where those actual periods are located in that visual representation. Now getting to speed here, speed is when it comes to light waves, refers to how fast the electromagnetic wave travels through space or a medium in a vacuum. Think of it like outer space. The speed is a universal constant. It's denoted by the letter c, and the speed of a light wave is linked to its frequency and its wavelengths by the equation c equals frequency times wavelength. We see this kind of example here of our higher frequency, smaller wavelength, our less frequency, and our bigger wavelength. Because we got higher frequency, we're noticing that those waves are smaller. And down here with that lower frequency, we have a longer wavelength. But the product of the two is always equals the speed of light in a vacuum, which is why if we follow kind of that little red area here, that little star, we're noticing that's basically staying basically at the same point, despite the difference in frequency and wavelengths. Because they are inversely proportional, they're equating to the same, which is c, which is the speed of light.